Hello. Okay, so I'm going to talk about parameter sniffing. So I've provided you with two files here. We've got a setup one. You just run it. What it will do, it'll take, on my machine it took 2 minutes. It'll generate a user table, a post table, some numbers, and a country. The primary tables we're concerned with is user and post. And we'll just start using this data. So we've got 1 million users, and I think we've got around 10,000, possibly 10 million to 100 million. Let's have a look actually. 10 million posts. We've got 1 million users and 10 million posts. So yeah, I've run this to set it up and it's generated this data. Ignore this one, this is legacy stuff that's not in this. So you just got country, numbers, post and users. Numbers was just used to help generate the seeded data. So we'll jump straight in. So parameter sniffing. So we will go through what parameter sniffing is and provide an example of it. We will also look at possible solutions. Parameter sniffing happens when SQL Server stores a parameterized query in the plan cache. SQL Server does this so that it can be as efficient as possible. Generating new plans every time takes resources, so it takes CPU and time to regenerate a plan every time. But this is what some database systems do, like Postgres. More advanced and more powerful databases want to cache planned data to get the extra performance, so it doesn't have to use CPU and time to regenerate that plan cache every time. This can happen for stored procedures, entity framework queries, basically any SQL query that takes parameters. Okay, so the data set we will be using, even though I go through it, I still get typos. The data set we will be using is a simplified Stack Overflow where we have a table of users and posts. The users also have a reputation like Stack Overflow. So a lot of this I got from Brent Ozar, so got to credit him for teaching us all great stuff. Hopefully I can help teach people as well. Spread the word. So let's have a look. We've got a users table. So the users, we've got 1 million of these. I'm just selecting the top 10. Have a first name, a last name, when they were created, a reputation, a location, and a bio. But because it's test data, it looks a little bit, auto-generated. But that's fine. It's good for what we need. If we have a look at posts, we can see here in this table we've got 10 million. I'm just getting 10 again to show you a post has an ID, it's mapped to a user, it has a question, and it also has a created date. With this data I can hopefully show you parameter sniffing in action. So here let's join them together. So again, select the top 10. For user 1, so we're saying for user 1, join on posts and find their posts. So this user has 4 posts, which are here. So they've written, some sort of posts. We've got post IDs and they're linked to user 1. So that's sort of how the data hangs together. Okay, so let's make sure that the database is in 2017 mode. We do this to turn off newer features which confuse the results, like adaptive memory grants and adaptive joins. So if I execute that, we should be in SQL Server 2017 mode now. I believe you can look at it. It might be database level, I think it is. General. It's in here somewhere. Options maybe. Yeah, there you go. So compatibility level is set now to 2017. So first do that before we go through this. So you can run through this and hopefully see the results for yourself. So before we get started, let's look at how SQL Server gets its statistics. It may be useful to know. So yeah, I find this really interesting, the statistics. So when we first query a row that has never been queried, SQL Server needs some sort of starting ground to estimate the plan. I have already done an update in the setup script, so you will see the user already has 2 statistics. So let's open up the user table and we look at the statistics here. So imagine we ran this query for the first time with the execution plan on. So I'll put the execution plan on here. You can also do Control M and I'll execute it. So what this is saying is find me all users where their location is United Kingdom. So we've got 3,949 rows that are United Kingdom. So how is SQL, let me just refresh that, how is SQL Server estimating the number of rows? So actually let's have a look here. If we hover over this, we can see estimated number of rows for all executions. I can't move my mouse over it, but it is 2, 4, 6, 7th and 8th. From the bottom, you can see estimated number of rows per execution is 4,018.78. So that estimate has come from somewhere. So where is that estimate actually coming from is what we're going to look at. So SQL Server estimates the number of rows. You should see that that SQL Server has created a statistic, something like this. And here we go. We can see this is a statistic it has created. Now the numbers will differ from your system to mine. So just open up the statistics and you'll see yours. So WA in the name stands for Washington State, where Microsoft is located, and SIS is the system generated statistic. The important thing to note is the 6 at the end of this long number. This signifies that it was the 6th column. So there's a statistic created on the 6th column. In this case, that is the location. So let's just select from users. That's fine. If we look at the 6th column, 1, 2, 3, 4, 5, 6. So that's the statistic. It's created for us. So in this case, I'll just read this. The import, signifies that it's 6th column. In this case, that is the location. So the first time we run a query on that column, SQL Server generates a statistic. This would be true for any other column. If I went and queried on first name, you would see a statistic similar to this, but with a 2 because it's the 2nd column. We can delve deeper into it. So what I'm going to do is I'm going to get the name of the statistic and copy it. I'm going to paste it in here. And I'm going to run this. So what we can do is we can look inside a statistic as follows, with the dvcc show statistic with the table name and the statistic name. It displays the data, location in this case, as a histogram. A statistic is an 8 kilobyte file and it only stores 200 rows. So anything in between an actual value may be less accurate, but this is generally okay. So what this is saying is if there's a country between, let's look for United Kingdom, it may be in here, it may not. Yes, it is. Let's say Uruguay or something. If it fits between that and that, it would use, I think, the equal rows bit here. So this is basically where SQL Server gets the statistics. So for United Kingdom, it thinks there are 4,018.778 rows. And we can look at this. So yeah, if we look at the United Kingdom, we see there's a row in the histogram. This number will be the number you see in the execution plan under the estimated number of rows. This may vary as the second time of running. I could not directly see, so you might not see it. It might fall between another one. So because there's only 200 rows, you know, there have to be countries that fall between it. If they do fall between, they will use one of these rows anyway. We can figure that out if we wanted. But yeah, this is where the statistic is coming from. So we can also see the rows sample is not 1,000,000 rows. So there's 1,000,000 rows in this users table, but you can see here it's only sampled 38,672. This was because it would take SQL Server longer to scan 1,000,000 rows. So it did a poll. It got a subset of data, 38,672 rows, and based on that it worked out the statistic. If you imagine you've got 1 billion rows, you don't want to scan through every one in order to build up a statistic. You just do a general poll to see, you know, on average it looks like there'll be this many rows. So let's tell SQL Server to do a full scan and see what the results look like then. So at the moment you can see United Kingdom is 4018. That's how many rows it estimates are in there based on this row sample set. We're going to rebuild the statistic, so I'm just going to copy that, paste that in there, and this is the command update statistic on the users with a full scan. So let's run that. And that's completed. Okay, so let's look at it again. Run this command. And here, now you see row samples as 1,000,000. So if we find United Kingdom again, United Kingdom, there you go. Now we've got no point values. This is an accurate because it scanned every row. So there are actually 3,949 rows that match United Kingdom. After running this, you can see the row sample is 1,000,000. So please don't think this is the answer that you should do. It's just showing you how statistics work. Statistics are updated when your table grows 20% plus 500 rows. Well, that was the rule of thumb in the past. Quite often your statistics, if not updated, can heavily skew what SQL Server will do. Because SQL Server is clever, it uses these statistics to, allocate memory. Should it use an index? Should it scan? Should it, lots of options. So in the case of creating an index, it has to do a full scan of the table to create the index. So at the same time, it would do a statistics as it makes sense to do so. So what I'm saying there is if we created an index on that column, a non-clustered one, we would get a statistic like this because it has to scan every row anyway when creating the index. So whilst there, you might as well create the statistic. So let's run the original query and see if the estimated number of rows has changed. So you can see here United Kingdom 3949. If we run this with the execution plans on again and we hover over this, if we look at the estimated number of rows per execution again, which is 2, 4, 6, 7 and 8 from the bottom, you can see now it's 3949, which matches what we saw in that statistic. So that's where SQL Server gets its statistics from, and hence helps drive the execution plans, the plan cache and how it decides. In this case, it's gone parallel. If we hover over it, it has scanned estimated number of rows to read, estimated number, it scanned all the 1,000,000 rows, which we can see is 6th from the top, number of rows read 1,000,000, but it brought back 3949. So hence it went parallel. It's also recommending a non-clustered index, which might be good, which we may actually make in the next step. Okay, so as you see, the new and more accurate statistic now says whatever it says instead of that one. And as I say, the number will vary every time you run this. It'll be slightly different because my data is random as well. Right, this is important to understand as every query that SQL Server runs uses statistics and the cardinality estimator to work out the best plan for your query. If it sees that it will need to do 1,000,000 rows to get 1,000,000 rows, then it will most probably want to go parallel, like this one has, and may as well do a clustered index scan, which means it just has to scan every row. But if it just sees it will need 10 rows, then it won't want to go parallel. In this case, it would most probably also do an index seek. So quite different approaches based on what you're asking for. If you ask for 1,000,000 rows, you'll most probably do a scan. And if you want 10 rows, a seek is going to be optimum. It's just going to seek to those rows. And a seek is dependent on an index quite often, either the clustered, your primary one, or a non-clustered. Let's continue with the actual parameter sniffing. So I've shown you statistics, which is really, really rather useful. So moving on, yes. Okay, so below we will have a look at the data we have generated using the parameter sniffer setup script. So that's what I've already run here. This is the one I've run. So let's just have a look at the data for the most popular locations. So what I'm going to do is I'm going to select the location, I'm going to group by it, and then I'm going to count the number of users. So if I execute that, you can see that United States has the most number of users, and as I scroll down, becomes less and less. So if I scroll to the bottom, what we've got Zimbabwe with 1, everyone else has some data. So we've got a big sort of part of the data, United States, we've got Zimbabwe with 1, but also I've made Zambia, which has no users, hence we don't see it on here. Excuse me. So that's just to show you sort of the distribution of data. We've got 61,000 rows users that are United States. Everyone else is, below 4,000 users per country, and then small data is Zimbabwe. And this will come in useful in a bit. It's all about your data distribution, big data, medium, and small data. Let's also count the reputation. So users have reputation, so we're going to group by the reputation. So if we look at that, we can see users with a reputation of 1, we've got 40,000 of them, and 5. Users with a reputation of 2, we've got 10,007. And then users with these reputations, we've got 25. If we scroll down, we've gone all the way to, user with 83. We've only got 1 of them with that reputation. So this is across the million rows that we've seeded. Again, you're finding your big data, your medium data, and then your small data. So right, let's create an index on the reputation then. So here we create a non-clustered index, ix reputation, on the reputation. I've also provided the drop one if you want to delete it, but we'll give that a second to get generated. Whilst it's being generated. So now we have looked at the data and set up. Let's turn statistics and IO and time on. Also turn on the execution plans, which we've already got turned on. So once that's done, there you go. It took 21 seconds to create that index. I'm just going to turn on the statistics with this command, set statistics IO and time on. So now let's write a query. So let's presume you want to write this query. You want to get your top 10,000 users where their reputation is equal to something, ordered by their last name. So let's run that and see. So we have got 10,000 rows from a user where reputation is 2. Yep, ordered by the last name. So let's look at the execution plan. SQL Server. That's a bit better. So SQL Server decides to use the index we just created, ix reputation, which was created. So there you can see it there, just to the left of my mouse. Hopefully you can see my mouse. So it seeks to the users who have a reputation equal to 2 and reads them all. It does a key lookup, which is this one here, 110,007 key lookups. So once it's got the ID, it then does 10,007 lookups to get the rest of the data. Because we're doing a select star, we need all the data. We can't, all that index ix reputation has is the reputation and the user ID, which is the primary key of that table. So in order to get the rest of the data, it does this lookup. And I believe we can hover over that and you can look at the output list. So you can see it's asking for first name. I'm looking just here on the right of the output of the mouse output list. You've got first name, last name, created date, location, and bio. So that's taking that execution plan. It does a seek, which is great, uses our index, and as you can see, it's reasonably fast. The actual finding the rows took 6 milliseconds. Well, let's have a look. SQL Server decides to use the index. Yeah, it seeks to the users, whoever it does a key lookup, as I said. As data, it needs, as the index is not a covering index, as I said, it's only got the reputation in it and the user ID. this is fast with the following statistics. So again, my statistics were specific at the time I wrote this. So if we look at the statistics that have been output, we can see CPU is 109 and the time to run in this case was 459. So, and logical reads here, there you go. So logical reads, it read 40,688 pages, which are 8 kilobyte pages, in order to get this data. It's a little bit slow, but we did ask for 10,000 rows. Another thing to note is when you have the execution plan on, it will slow down the numbers on here, but it's a great tool, the statistics. So let's do the same query with reputation 1. So this is us testing our, big data, little data. So here we've said reputation 2, which wasn't our biggest data. If we have a look at our biggest data again, if I run that, we've just asked for 2, that had 10,000. But now I'm going to ask for, give me the users where their reputation is 1. So, yeah, this one. Execute. Let's have a look. Okay, now that plan looks different, doesn't it? I will zoom to fit. So what we see, looking at the execution plan, SQL Server chooses to ignore the index on reputation now and starts scanning the clustered index, the main table. Here you see it's doing an index scan at the bottom right on the PK user, which is the clustered index table. It reads all rows and sorts by the last name. Note that it also goes parallel, so we've got these racing stripes. We can see that it reads all rows, so 6th from the top it says number of rows read, 1,000,000. The 7th one down it says actual number of rows, 40,005. So it read 1,000,000 rows in order to bring back or find 40,000 rows. And as you can see here, it's got the racing stripes. So let's look at the statistics because they're going to be different than the ones I wrote here. One thing I didn't do is the memory grants. So let's look at the memory grant. The last one supposedly had a memory grant around 50 meg. Let's have a look at this one. Memory grants, we can see if we hover over the select. So yeah, this memory grant says it's 207 meg, which does match the last time I ran it. So allocated 207 meg to run this query. If we look in the messages, we can see CPU, it took 797 seconds, and elapsed time, it took 557. So based on that, CPU is more than time, so also that's a pointer it went parallel, which we can see by these racing stripes. Okay, so we've done CPU time. Oh, and logical reads. Logical reads 130,893. So that's how many 8 kilobyte pages it had to read in order to get the results. So from this, you can see that there was a tipping point where SQL Server decided it would be more efficient to scan the whole table, our users table, instead of us using an index. Correct that. Index and look up all the extra fields it needed. So the previous one, if I just run the previous one again, you'll see it's different than this execution plan. Yeah, it does a seek, it does the lookups, and it's out of there. Whereas this one decides there's a tipping point where I'm just going to read too much data, so I might as well scan the whole table. But as you see, all that's different is we're passing in a different reputation, and this is sort of the basis of parameter sniffing. So from this, you can see there's a tipping point where SQL Server decided it would be more efficient to scan the whole table instead of using an index and look up all the extra fields it needs. You have seen the same query produce different execution plans. Let's now put this query into a stored procedure. So this is where we start parameterizing it. So I've called it get top 10,000 rows by reputation, and you pass in a reputation, which is there. There's your parameter. So let's execute that. Yeah, that's in. So let's run the query where there's lots of users with a reputation of 1. So this is where we start feeding in large data, medium data, small data, and seeing what it actually does to our query. Does it produce parameter sniffing, which I will show you. So I'm going to execute this, seem to run fast, 10,000 rows. So this is us running the big one. So this is the one where it thinks I'm not going to use the index. I'm just going to scan the whole of that table, read every million row. And let's look at the memory grant, again 207. It's very, yeah, it'll be same as before. It's going to take, 656 milliseconds of CPU and 778 milliseconds of time. So let's try the median data set. So now we're going to try the smaller one that, if you remember, didn't do the scan, it did the index. But let's see what happens when it does this now. Okay. Yep, and again, I'll fit it on there. So as you can see, it uses the same plan as the one above. So the memory grant, the logical reads, the CPU. Okay, but if you remember previously when we ran it just as a SQL statement, it didn't do this. It did a lookup, which was more efficient. So let's try the smaller data set. So this one, all this has is 12 rows. There's not 1,000 rows, 10,000 rows to return. But if we look at the execution plan, in order to get 12 rows, it still scanned all 1 million rows, which is rather expensive. For such a small query, to get 12 rows, it took 200 meg of memory, 211 meg of memory. It did a lot of work to just find those. What we see is that the same plan is used again. Even though we've got an index on reputation, it didn't use it because of parameter sniffing. So what we see is the same plan is used again. We can right click on the select, so let's do that. Properties, open that up. And the execution plan, and we're going to open up parameter list. But what we see here, you see the parameter compile value 1, the runtime value is 72. So the compile value is the first time we ran that stored proc with 1, and that is parameter sniffing. Now that query is in the plan cache, or the stored proc, it's in the plan cache. It will use this even if there's optimum or better ones to use, but it saved the effort of running CPU and time to generate a new plan. Let me shrink that. So this is parameter sniffing in action, where the first execution of a stored procedure creates the plan cache. The next time the stored procedure is called, it uses the compiled value to get the plan, and hence you get the same execution plan, which may not be optimum as in the last case. This one we could have had an index on, and we could have used a seek to that reputation, and we could have just read 12 rows and got out of there. It would have been really efficient. So SQL Server reads all 1 million rows in order to get the top n items. In this case of reputation, there are not 10,000 rows. Now you would say that this is not slow either way. It does grant excessive memory, but completes in a fast time. But it's not optimum. You don't want 200 meg just to run this one query. You're going to need a lot of memory if you get lots of queries. So let's run it the other way round. So previously we've run it with the big data, so that we passed in a reputation of 1, which we had 40,000 users in. But what we're going to do is we're going to clear that from the plan cache. We run this command sp recompile. We're also going to run this, which you shouldn't run on a environment, or at least a production environment, because it clears everything. But I just want a clean slate in the cache. So let's run the small data plan first. I'm going to execute this. And if we look at so here's our small one that just has the 2 rows. What we see is the nice efficient small index. So we can see it did the index seek, and if you look at the number of rows read, which is the 6th from the top, it only read 12 rows. It got in and out. It didn't read 1 million rows. You remember the previous one read 1 million rows to just find these 12. Now it's just got the 12 rows. And it does 12 lookups. So it's really efficient, really fast. we can look at the execution, 0 CPU, and 74 milliseconds to run. And most of that is most probably the execution plan. If we didn't have execution plans, that would be even faster. So that's really good. And also 51 logical reads. If you remember the last one, it was 130,000 logical reads. So this is really efficient, this one. It's using the index, which is great. But again, we're talking about parameter sniffing. So let's now, we've done that one. Yeah, let's do this one. So if I execute that, we should see it takes a little bit longer this time. Now, when I originally wrote this, I think I had a disk drive. Although it is running slower today, maybe because it's a fresh one, and I haven't run this, but you can see that took 9 seconds. So let's see what it did. So memory grant's a good one, because we've only got a meg of memory allocated. Because the first one was so small, it allocated that amount of memory to the plan. But the problem is, if we hover over there, what's happened is it spilled, you can see warnings near the bottom. It wrote 9,750 pages to tempdb because we were only granted a meg, so it needed more memory really to run this. So I will read this. So this takes around 7 seconds. This used to take longer when demoing on disk. If I was to run this again, it may run faster, but this is a good example that this took 7 seconds. This is because it doesn't have enough memory allocated, hence the bang against the sort, which I've just shown you. So what this is doing is, this query is for seeking, but you see what happened here. It's seeked and it's found 40,000 rows, but then it's had to do 40,000 lookups as well, which is a lot of work, you know. So maybe a scan would have been more optimum. So it needs more memory to write to tempdb. It also doesn't go parallel, so if you remember, the other one went parallel, which it did before in the big data plan. It does more logical reads because of the extra lookups as well. As I said, there's 40,000 of these. This is now an issue, as the query used to take a second or two, or, you know, milliseconds really. You can imagine people starting to say on the front end, this used to run fast, or it was running fast yesterday. This can just be that the plan cache was cleared for that query due to memory issues, or someone just deploying a change to a table in the stored proc. The other way that it might get cleared out of the plan cache. So yeah, SQL Server uses memory, so if you run out of memory, it has to start clearing things out of the plan cache. So really you should have a nice amount of memory, which we quite often don't. So the first person to make the request will have their parameters cached. So if someone chooses a small data set first, then everyone after will get the plan cache, even if they want the big data set. So if we look at the properties on this one, parameters, we can see it's compiled with 72, which was the small data set. So reputation 72 only had 12 rows. Yet we're asking for the big data set, and we're getting this suboptimum plan. It's worth noting that if you didn't set the compatibility level, then you may get adaptive memory grants. What this means is that if you run a query a few times, SQL Server will adjust it. If it wasn't given enough or given too much, the problem with this is it's just become a roller coaster ride of constant memory changes. So what I'm saying there, if you've got adaptive memory grants on there, the first time you run it, it may maybe say I don't have enough memory, so the next time you run it, it'll allocate more. If it still doesn't, it'll allocate more, but then there'll be a point where it's allocated too much, and then it will reduce it. And based on the plan, if you pass a small plan or a big plan query, basically you just get a roller coaster ride of it's constantly adjusting memory. So how can we make this better? So you've seen two plans, one that uses the index, it's good for small ones, but one that uses a scan of the whole table for the big data. But based on the first execution plan in memory, that's what everyone else will use. So all your other people will currently be using this small plan, which, as you can see, yeah, it took about 9 seconds to run that one. So How can we make this better? So the first option is query hints. We can tell the query to always generate a plan for a specific value. In this case, we want the big data plan. I've never used this, but it's an option. You can use this option, optimize for reputation 1. So if I run that, and then I run the small plan, and then look at the execution plan, what we see is we get the big data plan, where it reads all 1 million rows and pulls out the 12 rows it needs. So yeah, and this is the key. It says optimize for number 1, which is the big data. So if we run the big data as well, we will see it use exactly the same plan here. So that's one way. You can force it that way. But there's more versatile below. So one that's very common, option recompile. So this will tell SQL Server to recompile the query every time. So as I said before, if you've got lots of these being compiled all the time, it's going to take more CPU and time, and it's going to degrade the throughput of your SQL Server. So ideally you don't want to stick this everywhere, but this can be a quick fix. But this will tell SQL Server to recompile the query each time. This is not ideal. As I say, every time a new plan will be created. If you have lots of users and requests, then you can imagine if we put this everywhere, then you would start reducing the amount of requests that SQL Server can handle. So I'm just going to run this. Here you can see we've put option recompile on the end, and I'll run this one. So if I execute this, we get the nice seek plan, and if I run this, oh, wrong window, we get the big data plan. So that has worked. The problem with this is it generates, as I said, compile time. So the more complex your query is. So here we can see compile time took 2 milliseconds, compile memory, and the actual compile time. So this is a very simple query. If you've got one that's 100 lines, have a look at the compile CPU and memory. And then, if it's 200 milliseconds to compile it, imagine calling that 10 times. You've then got 2 seconds of just compiling it every time. So that's why option recompile can be dangerous for queries that aren't executed that often, or you think, yeah, I wouldn't recommend it if it's called, hundreds, tens of thousands times a day, but it is an option. But that at least gives you two different execution plans, good and appropriate, the small data and the big data plan. So the next one is optimized from unknown. So this normally will give a middle of the ground solution, so not as performant as we might like in this case. In this case it chooses to keep using the index. So Brent Ozar refers to this as optimize for mediocre. So let's run it. Here you can see the option optimize for unknown. Execute it. Let's have a look what plan it gives us. So yeah, it's giving us the index, and if we do this one, it's also giving us that index, yeah, but we spill to disk in this case because we haven't got enough memory, it looks like, again. Yeah, if I run that compared to that one, you'll see that we don't get any spill to disk on the small data. So the other option, which I quite like, is my preference anyway, and I think Brent Ozar's dynamic SQL. With this approach we can handle different ranges such as big data and little data plans. This creates separate plans per path. In this case we will get 2 plans instead of 1, still better than recompiling each time. The drawback initially seems to be to add more complexity with SQL string generation, but this is Brent Ozar's preferred approach and I like it too. So what we can see here is what we've got is we declare an envarchar, a big string, and we build up the SQL as a string. The first thing that you might think is a bit weird is this. This is just a comment, but this is really useful to find it with SP Blitz cache. If you're looking for queries, you can look at the leading start of the query and you can see, this is specific for this stored proc. Then all we're doing is we're checking the reputation. If reputation is 1, the big data, just put this string in there, otherwise put small data. And execution plans are based on basically the string of the query. So if the query is different, by a character or a space, it will generate a different plan. So what we're doing here is forcing two different plans. We've got the big data plan, where we just put the comment big data, or small data, and then the query is exactly the same. Select top 10,000, where reputation, and then we call execute SQL with our SQL. We pass our parameter, and that's it. That's the syntax for calling dynamic SQL. So let's run that and see what that gives us. Okay, let's do that. Execute. So what we see is the small data plan generates the nice small execution plan with the seek. I will just have a quick look in here out of interest. So compile is 1 and 1, so it's half this. It's faster, it seems. Execution, and you see this one generates the big data plan. So doing the same thing, but we can now have two. We're not recompiling every time, but we have two plan caches in memory. Let's just have a look at that as well. Again, compiled is 1 and 1, so it seems optimum. So let's just run that again, just have a look. Wonder if it'll go to 0. No, it stays at 1 and 1. But that is sort of the optimum one. So, okay. So you've seen parameter sniffing. It's the difference based on the parameters. The first parameter you run, it sets up the plan cache. If you're not using option recompile or the other options or dynamic, you will be stuck to that plan, and it can be detrimental if you're querying small data, big data, the outlier data. That's where the group by syntax is really useful to find your outlier data. As a bonus, let's show you a worse one. So small data plans mean big data can get spilt to temp db. So yeah, small data plan goes in and a big query comes in, the big data, what it has to do is spill to temp db, as it wasn't allocated enough memory. Big data plans mean small data plans get allocated too much memory and may do scans which could cause very slow queries. It's all about the tipping point and testing, as I say, the outlier data. So it's always good to use a group by to find, an account to find your biggest data set and your smallest data set, and test those and your sort of middle data set. This is all dependent on the query being written. For this example, I create the following indexes. So we're creating an index on location and on user ID. So a post has a user ID. So let's just create those two and wait for it. Right, so those indexes have been created. Let's have a look at them just out of interest. Refresh. So we've now got one on location and one on post indexes. Yeah, so there's our indexes. So now we've got those indexes, we want to get the top 200 users from a location ordered by post creation dates. So we've got a location, we're passing in a location like United Kingdom or United States. We're going to select the top 200 from posts in a join on users where the location is like that, but we'll order by created dates. We're going to get the earliest, the latest ones even, not the earliest. So let's just run it and see. Right, so we've got the big data. We know United States has the most locations from the query we ran at the beginning. If I execute this, let's see what it does. Let's look at the execution plan. So it's gone parallel. We can see racing stripes. We can see the user table, the post table. It's doing some lookups on post. But let's run the middle one, see what that does. So this is us putting the big data. So I think the important thing to take out of this is hover over this and we can see memory grant. So our memory grant to run this query is 3,178 meg. So it's 3 gigabytes of memory to run this query. So, you know, if you got 30 gig, you can only run 10 of these at one time, and then you're out of luck. You're blocked until they can execute. So I think that's, yeah, if I remember correctly, that's what this is showing. This is the big data plan going in first, so we get this big execution. You see that the lines are very small here, so there's not much data. But again, if we look at this, we can see that 3 gigabytes, which is the 5th column from the top. Memory grant. So as I say, all ran fast with big data plan. It just wanted 3 gig of memory. So this can vary. So I ran it yesterday on another machine. It only took a gig, but yeah, this is behaving and showing us the 3 gig. Let's clean the plan cache for that stored proc. Let's spin it round now. So previously we loaded it with the big data first. Let's load it with the small data. So the small data one looks nice and optimum. Look how thin those lines are. It's really quick. It's doing an index seek, a lookup, another seek, another lookup. So seeks are really good and efficient. We can see it's taking very little time. You know, 47 logical reads, 7, very small. And again, yeah, 0 CPU, 64 milliseconds of time. So it's reasonably fast. It is fast. So let's run it for the bigger data sets, just see how long. So that seemed to return okay. Now our lines are getting fatter. You see, we're returning 200 rows. Yeah, but we're starting to get more data now being read. Let's run this big data. So this one, these have about 4,000 users. This has 60,000 users if I remember correctly. Let's just have a look again. Let's rerun that query. It's somewhere up here. Need to find the grouping. Yeah, location. Yeah, 61,468. So let's see what happens. Execute. Okay, so it's taking its time now, isn't it? Okay, so let's see. When I ran this yesterday on my other machine, it was fast, so it's behaving slowly, which is good for this example. So what we find is that when the small data plan goes in first, the big data plan uses it. It spills to disk a lot and takes longer. So it seems to take a minute previously to complete, spilling 39,000 pages to temp DB. But what I found recently is with SSDs, which this machine has, but it's sort of a fresh setup of this database, so maybe it's not in memory. With SSDs, these examples run faster. Originally, ones were much slower with disks and older technology, but parameter sniffing is still a thing and can arise when you have very diverse data. So you should focus on the outlier data when investigate a possible parameter sniffing issue. So by that I mean the outlier data, you know, in this case United States, Zimbabwe. So United States was our big data, Zimbabwe was our little data, and anyone in the middle in this case. But this is actually took 1 minute and 8 seconds to run, which is very close to the original I ran a good while ago. So let's have a look at the query to just see if we can understand. So it's getting all the posts, getting the users, where the user location in this case is United States. It's put in, remember it's put in the small plan. But these lines are fat now, and you can see here it looks like it's spilled to disk. Yeah, if you look at the warning, 38,000 pages were spilt to disk basically because it didn't have enough memory. So you've seen the big data go in where it allocates 3 gigs, small data where it doesn't allocate enough, and that's when it bites the big data query in the bum because it hasn't got enough memory, so it has to spill to disk, and then it becomes really slow, you know, taking over a minute when this one is instantaneous. And that's all because that plan is now in the cache. So as I said, there are ways around that with option recompile or dynamic SQL would be my option. But yeah, if we look at this query, it's getting posts, users. So it's finding all the users in that location, United States, and there's 64,000 of them. So it has to read all of those 64,000. Then it has to order the created by. So it has to do a lot of lookups. So if we can see that the sorting here seemed to take the most time. Let's have a look. So we start from the right and work left. You can see 0.183 milliseconds, half a second. Here's taking 2 seconds. So it's the sorting that took over a minute, 1 minute, 4 seconds, just to do all the sorting to figure out, because how many did it have to sort? Oh, that's the output. How many did it have? Yeah, so it had actual number of rows, 615,000 rows. Because this isn't users, this is posts, so there's 10 million posts. So of those 65,000 users, we had 615,000 posts. So it had to sort 615,000 in memory based on the created date. And I believe that's why we didn't actually add an index on the created date, so that could have maybe helped it as well. But it goes to show you the big data and small data. As I said, big data goes in first. It creates excessive amounts of memory, may run fast, but you may not be able to run many of these because you run out of memory. Or your small data goes in first and you don't have enough memory. But as I said, there are options. So what we find is the small data goes in first, the big data plan is used. Yeah, so with SSDs, I've mentioned that as well. So one other thing, you can also use SPBlitz suite of stored procedures and SPBlitz cache stored procedures to monitor the performance of these things and drill deeper into them, which is a really good set of tools. I have done, or I will do a video on that. So what have we learned? Statistics are how SQL Server can estimate the number of rows it will get back. Good estimates provide good memory allocation and plan execution. So hopefully you found the statistics really useful and you can use that. Bad estimates can cause poor plan generation and totally wrong execution plans. So it's quite a good idea to have a script that updates your statistics, once a week, once a month, not every day, because that can introduce parameter sniffing. If you rebuild statistics, then your plan cache gets kicked out, and the first person that comes in the morning runs a query, your manager, and he runs a big query or a little query, and then that affects everyone else. So yeah, weekly to rebuild statistics, or monthly. Most probably weekly. I'm not an expert, but there's specialist scripts for that. So parameter sniffing is everywhere, but we only notice it when we get vast differences in the data coming back, as in the outlier, big data, small data, as I've shown you, generates different plans. If small plans go into the plan cache, then they will affect big data plans as they spill to tempdb. If big plans go into the plan cache, then it will be granted excessive memory, but this may be okay. Have you got enough memory? You can't always preempt when to handle parameter sniffing. This happens later on when you get larger data ranges. Big with lots of rows and small with a small number of rows. How we help SQL Server out with query hints optimization for unknown, option recompile, and dynamic SQL. But hopefully that showed you the general concept that parameter sniffing can be everywhere, and as your big data and small data vary so much, you can hit this. But I've provided solutions to get around this and optimize your queries for specific data sets. So I hope that all made sense, and I think we're done. So thank you very much. Cheers.